Welcome to another episode of Lineman Talk. Today we're going to spend a few minutes on my favorite subject, distribution power transformers. Do you know why transformers hum? Because they don't know the words? Here we have a brand new transformer, cutaway demo model, never been filled with oil, but if it still had all of its parts and it had oil, we could hang it on a pole. This is a little 1.5 that failed. We untanked it, identified the parts that gave up, and we're going to use it as part of our demo. I received a call the other day. The young man said, I'm using my own meter and the distribution transformer that I'm having trouble with is blowing fuses. I said, well, don't use your own meter to check for a shorted winding in a distribution transformer. Your own meter has value looking for a open winding, but the readings you get from an ohm meter on a transformer coil are unreliable. Let's test these two. So here's a Fluke 87, one of my favorite digital multimeters, set on ohms. This is a brand new pot, so we're going to go X1 to X2. 35 ohms. X2 to X3, 22 ohms. And X1 to X3, 90 ohms. None of that makes any difference. You can see that we went across the coil in the center tap, ground straps on, but the secondary coil is isolated. Here's the transformer that we know is bad. X1 to X2, 0.6 ohms. I want to do X2 to X3, 0.1 ohms. And then we'll go from across the full coil at X1 to X3 and we read 0.6. So using a digital ohm meter to determine whether your transformer coil is shorted is the wrong way to do it, in my opinion. This transformer, we know, blew the high side jumper out. And a test from here to case would show you open. You already blew the fuses, so you're taking that pot down, but if you were doing forensics, you could try to determine what happened. We keep this one around for a little cutaway to see how the transformer's put together. We keep this one around for a little cutaway about how the transformer's been put together. And the correct instrument for that type of winding resistance test can cost you $20,000 to $40,000. It's not going to be the same as my $500 Fluke 87. There's other ways to do that. In a minute, we're going to set up here and we're going to talk about winding resistance and how the transformer works. But give me a second to set this table up and we'll be right back. All right, we're set up to demonstrate the next part of this lab, this video. And what we want to do is show magnetic coupling. That's how the transformer is going to work. In this demonstration, we have a 500-foot roll of number 12 copper that we're going to use as the primary coil. We have another roll, 500-foot number 12 copper, we're going to use the secondary coil, and then our core will be this steel rod. When we measure resistance on this roll, we come out at 1 ohm. And using Ohm's law, it would say if you were passing DC across it, you would pull 120 amps. But because we're going to apply AC, 120 volts, this roll will become an inductor and will bring an impedance beyond just plain wire resistance. I put a couple boxes of paper clips here, and you're going to watch when we energize this coil. And usually young men say, when you energize this, you're going to trip that 20 amp breaker. I say, okay, let's see. So we plug it in, you start to hear this vibrate, and you watch these paper clips jump out of the box, literally jump out of the box. This becomes the high side coil of our transformer. So in a lab like this, what comes first? Safety. So we have a hard hat as part of our uniform. We have our rubber gloves that we're allowed to use on 120 volts. And then we have our protective eyewear. So give me just a second to set all that up, and we'll be back right here. Okay, hard hat, eye protection, rubber gloves, 120 volts. We're going to energize this coil. When we measure amps on this coil, unloaded, roll of wire only, pulls 31 amps, not 120. So now we're going to move these paper clips out of our way. And we're going to pull the secondary coil near the primary coil. There won't be any core, and what you'll see there is pure induction. Now behind me I have 3 light bulbs, and I'm going to try not to block those. They're tied to the output transformer right here. So we'll energize this and then start pushing the secondary coil toward the primary. And you'll begin to watch those bulbs burn from pure induction. So you can see the light bulbs are burning. There is no steel core. We're taking this magnetic field, and because this one is so close, we're just inducing this to the secondary coil. Let's see how much air gap we can put in it. Just an inch or two. Now, I'm going to move away, and I'm going to insert the steel rod, which will become the steel core of your transformer. Pass the steel core through the first primary coil. Now we're going into the secondary. And we start to see the lights burning. When it was pure induction, those lights wouldn't burn. Okay, right now we know what's happening is we're coming from this magnetic field into the steel bar into the secondary coil. Now we're going to close the air gap. Now this is a very poor transformer, very poor. This steel rod is getting red hot on the inside. Red hot. this energy loss from eddy currents and just core losses, call them what you want. This rod is getting into hundreds of degrees, and I'll insert a thermal video showing that. So right now I'm going to disconnect this transformer. The thermal camera will show this rod. Right now it is too hot for you to touch in the area where the primary coil was located. We're going to push the secondary coil away and stop that induction. The primary coil is still energized. And we're going to disconnect the transformer. So this is easy to do. 500-foot coil of wire, 500-foot coil of wire, 120-volt cord, just end to end, black and white. We tie this to our load. The output with this very poor transformer is about 40 volts. So when you saw those light bulbs burning, that was 3 12-volt bulbs in series. So when you saw them got real bright, as soon as I got them close together, I was probably producing about 40 volts. When we loaded it with 3 bulbs, the primary had 16 amps on it, and the secondary had 3.3 amps. Remember, these are 500 footers, so on paper they were 1-to-1 ratios. The next thing we're going to do to show you that this was a magnetic coupling is we're going to use an aluminum rod. We're going to replace that steel core with an aluminum core. And because aluminum is non-ferrous, we won't see it work. So I'll re-energize this coil, put the steel core in, make the bulbs burn, pull the steel core out, insert the aluminum core. Nothing's going to happen because the aluminum cannot create the magnetic coupling required to energize the secondary coil. High side transformer is energized. Steel cord gets inserted. See the bulbs burn. Air gap I got right there. Now I'm going to remove the steel core. Now we're going to install the aluminum core, the non-magnetic, non-ferrous material. There's no light bulb, there's no attraction from this high side coil to the aluminum rod. All right, we have everything disconnected. And I think what we've done, we've got a pretty good job of demonstrating the magnetic coupling that's required to make a transformer operate. We've talked about the inductance that occurs when we energize this coil. It becomes an inductor. And then as we get this air gap, so when we talk about induction out on the line, how much current's passing through the wire? How close are you? How long does it stay parallel? There's quite a few variables, but the part that you've seen here is that the steel is required. Now, I'm going to lift this transformer coil out of this burn-up transformer and show you. This transformer doesn't look like our transformer. When we're learning about transformers, we read through the books and we see this square coil and there's wire on this side and wire on this side, and that's very inefficient. Here's a transformer coil that I built, 2-to-1 turns. It's so inefficient, it creates so high currents in the coil, it won't run on a 120 volt circuit. All the manufacturers are trying to build an efficient transformer. They're using laminated steel core plates here, but the secondary coil and the primary coils are actually wrapped around each other. They're not separate like this. Wrapping around each other increases the efficiency. There will always be losses. We don't have a superconductor, and we're going to see core losses, iron losses, and until they can create a core material that's better than this, we're going to continue to see that. We'll see eddy currents, we'll see losses, and right now, of course, this one's burned up. It's a little dirty, nasty. We cleaned it up the best we could. But it's nothing but wire around more wire. And until it's energized, it's just wire. If we ran it out in a straight line, it'd burn up. There would be no magnetic field created. I want to thank you for your time, and I'll see you in our next episode of Alignment Talk.